Hi guys, now in this video I'm going to be looking at some counting techniques and show you a couple of examples of why it's really useful. Now I don't know if you've ever been in this situation, but you've got a combination lock, and I had an old one at home and I forgot the actual code for it. So I actually had to try, and rather than throwing it away, I thought I can get the combination by doing that. So if we were looking at this example here, so let's say you didn't know the combination, how many combinations would you need to check in order to actually work out what it is? So we've got numbers 0 through to 9. So if we were looking at the first barrel, how many different combinations are there? Well, there are in fact 10 different combinations, right? And then what we're going to use is a thing called a product rule. The next combination, there are also 10 different combinations, and then there are also 10 different combinations. So if you were trying to break this lock and you didn't know what it was, there would be 1,000 combinations. All right, now that's the general thing that you'll see with a cheaper lock would be 10, like it'd be 3 combinations, 3 barrels. And so therefore for someone to find or pick that lock, they'd need to know 10,000 1,000 combinations. Now the reason 1,000's okay is most people wouldn't sit there for the time to do 1,000 combinations, because then they'd be seen by someone breaking into the lock. All right, so that's probably okay for most things. How can I make that lock more secure? Well, if I had another barrel on it, then that would make for 4 different barrels. Then it would be 10,000 combinations. That would be much harder. Now, you might have seen something like if you get a credit card or a bank account, thing like that, generally they have a 4-pin number. So a 4-pin number would mean for someone to work out your particular number, if it was just a number, then that would be 10,000 combinations. If it was you were using letters, then it'd be a 4-pin letter number, then a 4-pin sort of combination, won't call it a number, then that would be 26 times 26 times 26 times 26. All right, or we could say that's 26 to the power of 4. How many would that be? Well, 26 to the power of 4 is 456,000 combinations. So let's say it's 460,000 just for ease of what we're doing here. So that's approximately equal to 460,000 combinations. See, it becomes a lot more complex and a lot more difficult to do. Now here's a problem that would confront a lot of people, like in government, is that we need to have number plates to identify cars. Right, so we don't want to run out of those things. So what they did was they used to have just numbers before, and then they introduced letters. All right, so with this combination of number plates, you've got 26 for the first combination, you got 26 for that next combination, you got 26 for the next combination, and then you have 10 by 10 by 10. So if we do that in our calculator, right, so that would be 26 to the power of 3 times by, well, delete that, and then times by 10 to the power of 3, or I could just say times by 1,000, that's what that would be equal to. That's going to give us 17 million possible car combinations, right? So 17 million car combinations, 1757000. I think it was another 0 in there, wasn't there? 6. All right, so that was a 6, and then another 0 in there. So that's a lot of combinations. Okay, when we start looking at that means that we could have 17 million cars on the road. Now, if we had more cars in there, how could we easily change that to make it a bit more, to compensate for more cars? Well, if we introduce another letter, we times that number by 26. Okay, we've now got 456 million combinations. All right, so that's sort of, you see the complexity how we can get things to be more difficult there. And again, another one is with mobile phone numbers. So you think about mobile phones and having a unique number. So every time you go get a new mobile phone, you used to have to get a new mobile number,